Thank you. So, I wanted to talk about a little bit about how where I'm coming from. So, as Ken said, yeah, I work on the garbage collector for the JavaScript engine in Firefox, and that's one of these things that people come up to me and they say, "Oh, gee, you must be super smart and crap." And I feel a bit like this guy because I also get excited about technology, and he gets excited and says nonsensical stuff, and this is, yeah. And it's because this stuff is fun that I can feel this way. So, but I was lucky. I got a couple of lucky breaks to get here, and yeah, my research work was one of them. I started programming when I was like 12 or something. So I recognise that not everybody. I'm not actually. Other speakers have held a microphone. Is everybody hearing me, or is this just working magically? What's going on? You're all hearing me? Cool. One of these things? Cool. All right, I can do that. Yeah. Yeah, so, and that's what happened. So, the part of the compiler, we're going to talk about code generation. I find that there's a lot of resources online about the earlier stages in the compiler, about parsing and so on. There's not that much about type checking, like really hard type checking stuff. At least accessible information is what I'm talking about here. But and so what we'll talk about is is actually generating code, which is cool. And yeah, so why should we talk about it? Like I said, it feels like it's one of these arcane things, like garbage collection, that only the experts know, and it's kind of a closely held secret. So, and you have to speak to Giles at the bookstore to get the book on it. Anyway, and here's what's happened. People talk about it and they say, "Oh, gee, that's hard," and they tell themselves that it's hard, and then they don't actually try to learn something. So the message here is to give it a shot, to try and learn this. So yeah, Mattel released a Barbie in '92 that when you press the button, it said math class is tough. And if you implant these kinds of ideas into people, then maybe they won't try. So while code generation might be difficult, it's worth trying, and yeah, challenging is a better word. Fun is also good. So yeah, and if you're not familiar with the Barbie, you probably are familiar with the Simpsons episode, so which is somewhat like quite good as well. So on the other hand, I don't want to say that it's easy either, because that has its own problems. So I don't want to spend too much time talking about easy and hard and the language we use. Other people have done plenty of that already. Yeah, so like I said, I prefer to say that this is fun rather than rather than hard or easy. So it can be rewarding. So anyway, and any topic is no different. I like to go downhill skiing. I've worked hard at that and I've gotten fairly good. I've also taken a 3-hour course in how to use a coffee machine and make a flat white. That does not make me an expert in making flat white. I've made one good flat white and 2 terrible ones in my entire career of coffee making. The bloke downstairs, or person downstairs, is much quicker. So you still got to work hard at something. Is my point there. Anyway, WebAssembly. So I'm assuming most people have heard about WebAssembly. There seems to be a fair bit of news popping up on Reddit and so on about this. But in case you haven't, it's an what do you call these things? It's an intermediate representation, which is a way that you can store a computer program that's not source code and it's not machine code either, and it's somewhat in the middle. So it's like the JVM, like LLVM, and .NET. So it's a way of storing code that's been compiled that is not quite ready to give to the machine. So WebAssembly's another one of these, but made for the web, so made to run inside browsers. It's an open format, and many companies are working together to create this format. There's already a MVP, or minimum viable product, available in the 4 most popular browsers. I guess they're the 4 most popular, but 4. So of the big browsers, I suppose it's IE that's missing. So that's missing support. But yeah, so 1.0 has landed, and you can use it today. Some languages already compiled to it as well. Most probably, notably, is Rust. So there's a popular language that can target it. Yeah, so about WebAssembly code itself. WebAssembly is stack-based. There are different types of machines, stack machines and register machines. And a stack machine works by storing intermediate values as it goes on the stack over here. So as it executes each instruction, it'll put something on the stack. This is not actually WebAssembly code, but it's close enough. We'll get to some real WebAssembly in a moment. So push a value onto the stack, we'll put it on the stack. So we've pushed 32, we're going to push 35 onto the stack. Even push 9 onto the stack, and our stack has grown to 3 things tall. So these are the temporaries that we're going to work with. When we execute multiply, it takes the first 2 items off the stack and replaces it with the result. So, and each operation can take or leave as many things as it likes in most stack machines. In WebAssembly, the only thing is that most things leave a single thing, or maybe 0 things. There's not yet support for leaving multiple things on the stack at the end of a single instruction. Like a single instruction can't put more than one thing. We're going to push our next value and then do a division. And one more step and we do the addition, and we've converted some centigrade degrees, I think it was 35 centigrade degrees, to 95 Fahrenheit. So, the data types that WebAssembly currently supports are integers and floating point numbers, both 32 and 64 bits. Fairly simple. There may be more to come, particularly types of structures and so on that you'll need later on. And like most machines, it's fairly common to use 2's complement arithmetic. That's what your CPU uses for integers. And that means that most operations, like addition, subtraction, and everything, are sign agnostic. It doesn't matter whether you're actually thinking of something that could be negative or not. What you actually do with the bits is the same. That only comes into play when you're going to say, is it greater or less than 0, or do a division, things like that. So only a couple of operations have specific sign versions, and they're represented by a different instruction. Also, floating point numbers have different instructions all to themselves because they're a different format, and you need something totally different. The one thing where you get a little bit restricted is that what you would use for a Boolean is an int32. So if you do is something greater than or less than something else, regardless of what the input types are, and they have to be the same type, by the way, you always get an int32, either 0 or non-zero. And then your branch instructions will take an int32 off the stack to do their operation. So here we have, we're assuming that x is already on the stack. We're going to push the number 5 onto the stack as an int32, as an int64. So x is an int64. We're going to put 5 on the stack as an int64. Our less than operation, LT for less than, will take those 2 64-bit quantities off and leave a 32-bit value, and then you can do the branch. So that's just, so in the hypothetical language that I've created for this talk, where I've actually restricted, it only has a single data type, and that's int32, and this is one of the reasons why. So why I went with int32. In WebAssembly, you get each instruction can either be an atomic instruction, so that's just like a constant like we saw, or add, or multiply, or so on. Or it can be a block of instructions, an if statement with then an else branches. If the else branch has 0 instructions, then it can be omitted. Or a loop block. And this is a little bit unusual for a machine code, very unusual for a machine code, and a bit unusual for an intermediate representation. Usually each function in an intermediate representation is just made up of a series of blocks with IDs, and you can jump from any block to any block. What's different about WebAssembly is that you can only either enter the block just from the top, normally, or you can do basically a break or a continue from within the block back to one of your parents, and any of your parents. But you can't do a goto from one place in your code to another place in the same function. That's not yet supported directly. So during compilation, if your source language has a goto, you have to do something else to get that to work. And the last thing I want to show you is an indirect call. There's a call instruction which, oh yeah, I didn't show you when I showed you the stack example, and you saw something like add, which took some things off the stack and replaced it with a single thing. Call instructions work in the same way. They take their arguments off the stack and replace it with their result. An indirect call will also take a integer, a 32-bit integer off the stack, and that's the ID of the function that you're going to call. And it'll look in the function table for which function that maps to, verify that the types match, because this is a safe language, it has to be to run in people's browsers, and then call that function. There's a few things missing at the moment. These things are likely to come soon. One of them is garbage collection. That's a biggie that everybody's waiting for before we can easily put languages like Haskell into WebAssembly. Because ideally you'll use the browser's garbage collector rather than ship your own. At the moment you could write a garbage collector in WebAssembly and ship that to users' browsers, but it means shipping more data to users' browsers over the network. And who wants to do that? Me. So yeah, I might do that, but you don't need to, and it's more sensible to integrate with the browser one, because having more than one garbage collector in the same environment is not fun either. So yeah, it's better that we just get that into the spec and enable it in browsers. Like I said, returning multiple values from either a block or a function is not yet supported, but that's hopefully coming soon. And tail calls and some other stuff. DOM integration, and that will go along with garbage collection. You need that garbage collection before you can do DOM integration and other JavaScript integration, because you need to interact with objects on the DOM, in the DOM and in the JS heap, and do the collection between the different environments. So there's also some stuff that I kind of put in this other category. I'm just guessing. I don't work on WebAssembly itself. There's some people on my team, so because it's kind of the same team within Mozilla. Like I said, the unstructured things, and I was actually really surprised. For a stack-based language, there's actually no dup instruction to duplicate the item on the top of the stack. If you've used a stack-based language like Forth or something, you'll have seen dup, swap, rotate, and drop, and maybe pick. And the only instruction of that set that we actually have is drop. So, but instead, WebAssembly has gotos, which some other stack-based languages don't have. So it can be, depending upon what you're translating into WebAssembly, that can either be easier or harder. So we've got a hypothetical language. Here's another look at the compiler pipeline again, and we're dealing with a language like the abstract syntax tree of our language, which is roughly here in the middle of the compiler. and it will go through our code generator, and our code generator is turning something like this into WebAssembly. Our functions are fairly simple. They've got names, they've got arguments, and they've got a body. And the body is an expression. And an expression can either be a binary operation, like add this and that, which are both expressions, call something, let a variable, use the value of this variable or a constant. And lit is short for literal, so it's a 32-bit literal value. It basically means it's a constant. And let to bind a new variable, and case. And now we've got a Turing-complete language. There's a few things missing, but it is Turing-complete. So, yeah. And for the case situation, you've got these other types. So, of a case, you've got multiple pattern and expressions in that. And each one is made up of a pattern to match against and an expression to execute if that pattern matches. And the patterns are really simple. They're either a constant number or the wildcard pattern. Notice I've got no pattern that actually binds a new variable, because you can do that with let. There's also no if as well, because you can do that with the case analysis. So you return a Boolean and then match on true or false using the case. An example program. Here we have two equations. Because, I did write a parser for this language, but we're not seeing it yet. But here's the in-memory data structure, a representation that you saw that matches the other one. It's in Haskell syntax, in case you were wondering. And here's it laid out, the abstract syntax tree laid out in memory. So, yeah, what our language doesn't have, I mentioned a few of these already. Another one is, higher order calls we don't have, and closures. Things that if I had a bit more time, I might have added, because this is a functional programming conference, so I'm sorry. So let's generate some WebAssembly. We've got a really simple expression. We've only got some types of the nodes in this expression, in this AST. And what we do, we start with a depth-first search. We're really lucky. What's cool about this? This is kind of your first code generator. And why it's a great example of going from a functional language to a stack-based language is that they fit really nicely. All we have to do is walk the tree, doing depth-first, left-first traversal. So we start here. The instruction that we need to do for this is to put the constant 9 onto the stack. The next one, we put the value that's in the x variable onto the stack. We'll come back to what getLocal does in a moment. And as we go up the tree, we just write down the instructions. And these instructions, due to it being a stack-based language, will just do the right thing because the context is on the stack. It's just a nice thing between AST and stacks. And so it's fairly straightforward. We can just keep traversing the tree and writing down the instructions. And provided that everything either returns... The only way you can mess this up is if something expects a different number of arguments than it's getting, or returns more arguments, like pushes more arguments onto the stack than its position in the expression expects. But you should have checked that with your type checker earlier in your compiler anyway. I didn't. In this compiler, there's absolutely no type checking. So, in fact, there's only one type, but there's still none. Yeah. So anyway, fairly straightforward. So now we want to talk about where this 0 comes from. How did we know to put the 0 there for getting this local? We saw in our abstract syntax tree that the parameters of the function were just strings sitting there waiting to be used. And in WebAssembly, we've got locals. So you've got basically a stack frame of locals. They each get their own number. So what I did, you could do it a bit differently. There's a few different answers. is make a traversal over the abstract syntax tree before I start generating code. And each time I see a let, I say, well, let x equals blah, blah, blah. Well, what I have to do is create a new numbered local for x. I also have to do it for the function arguments. They're unlike other stack languages, when you call a function, the callee will find the arguments in its locals rather than on the stack. Something like forth will find them on the stack already, but WebAssembly doesn't. Yeah, so this one, first in the red, it has to check that we haven't used this variable name already, because while we could have let something in something blah, 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 and then later on let the same variable in something blah, 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 that would work fine. But if we had them nested, we would clobber the earlier variable. So we can't do that. And like I said, this is a simple code generator. We're not doing SSA, we're not doing register allocation, or which would be local allocation in WebAssembly's case. So those are, you can do those later. And then when the variable is not unique, so I've skipped what actually happens here because it wouldn't fit on the slide. But in this case, we just have to make sure that we get a new variable ready to use and give it a number so that we can find it later. And those get put into a symbol table. So now we see how we generate code for a var node in our abstract syntax tree, and for a let node in the abstract syntax tree. So in var, all we have to do is look up the variable and write get local as the instruction with the right ID of the variable. And in the case of let, first we generate the code for the expression whose value we're going to get, and then we do set local, which will take that variable off of that value off of the stack and save it into that local variable. Then when we generate code, we can do the get local, and it'll work and play nice. So, and some of that works so well because we're lucky that WebAssembly is an easy language to generate code for. So, and in a case switch, this is probably the only tricky part, and again, because of WebAssembly, it's actually fairly easy because we have those nested instructions, like an instruction can contain more than one instruction. That not being true for other languages makes them a little harder. You would have to be generating a list of blocks and saving their IDs somewhere, like the ID of their labels. Yeah, so for WebAssembly, we have to get the variable that we're switching on. So we actually save that to a local variable. This was where I was surprised that there was no dup instruction. Normally I do a dup, and so that I've still got that old one on the stack, I've got my new temporary to test and see if it matches this case in this pattern. But instead, for WebAssembly, we've created a new local when we get to these nodes as well. And so that's what's being used. So it actually, we'll see an example later where it generates like some set local, get local, set local, get local, because it's shuffling things around a little too much. But you often see that in a code generator, and then we'll optimize that in a slightly later stage as well. Yeah, so that's the only slightly tricky one. So, we're ready for a demo. I like the slides because the slides are done in JavaScript in the browser. WebAssembly is running in my browser, and I can just demo it right here. I don't even have to exit my presentation. I can do 32 Celsius to Fahrenheit, and I get the right answer. And it ran in 0 milliseconds. I can do another computation. I'm going to do, actually I'll leave it on 32, and we'll calculate in WebAssembly that Fibonacci number, using the naive Fibonacci equation, which you can see here. This is the code for the language that I wrote for this presentation. Yeah, so that took 51 milliseconds. If I run it in JavaScript, it's not bad. Let's bump it up. 35. The 35th Fibonacci number, we can calculate just over 100 milliseconds. In JavaScript, It's a bit slower, but still not bad. We're in the ballpark. And this is, you know, micro benchmarks, they only test this benchmark. It's not actually telling you whether WebAssembly is faster or not. It's only testing this one. But you get the idea. 39. Yeah, half a second in WebAssembly. And a bit longer in JS. So here's the code that program generates in the code generator. And I find it on the screen here. Yeah, we can see the set local, get local, set local, get local while we're setting up the test for whether our variable is less than 2. So if I go back, if it's less than 2, we do this by, like I said, we have to set a boolean. It's still an int32, but it means a bool in this case. If n is less than 2, then test is done 0, or 1, I suppose. And we return 1. If it's... Why did I put 0 there? Oh yeah, because it's false. Duh! Yeah. Thanks, everyone. Yeah, then we go and run the computation. And so here, our local is in number 0. We have to compare it to 2, so we're pushing 2 onto the stack. Less than, signed, S is because we're working with signed numbers, because that's what I just did. Like I said, there's only one data type in this language. And now we need to save that, because now we're generating the case from this point on. So we save that as our local thing that we're going to pattern match on. Oh, we need to get it so that we can pattern match on it. And oh no, that's where we're binding it to the value test. Here's where we're generating the case. So we save it and then get it, and there's a bit of redundancy there. Like I said, it's a really simple code generator. It's not an advanced one. And we pattern match against 1. Is it equal? Well then, if it's equal, then go and do this. Push 1 onto the stack, and that's the end of the computation. If it's not equal to 1, then you go and do this. And I've actually got a bug here. We notice here, I matched against 0. If this was 2, if somehow a boolean was 2, then I would actually crash, because it would run this if my boolean was 2, where it should be throwing some exception.
Sorry, Paul, we're out of time.
We're out of time? All right, no worries. I want to say one more thing. It can be challenging, but like all of these topics, there's nothing actually there's no reason you can't do it, particularly a simple one. And you might spend, like I said, 3 hours of coffee making, and I can make it flat white sometimes. You can make a code generator sometimes. You've seen a 20-minute presentation, I'm sure. It's rewarding. You spend a lot of time on a lot of stuff. It can be rewarding and fun. Thank you.